Okay, if you didn't sit in for the live recording, or even if you did and you wanted to see this again, this is how you evaluate a terminal velocity problem. So an object that starts at rest and speeds up. The last one, the boat problem, we had an object that started moving and slows down on a force that depends on velocity. This one we're going to speed up. So what is terminal velocity? We'll answer that question, and we will solve for what the terminal velocity actually will be for an object, and then we'll solve for the velocity as a function of time. So this is our starting scenario. Take a ball or some other object to some large height, let go of it, and it starts to fall. And so far in this class, we've just represented this by our force of gravity acting down, m times g, and that's it. And we just kept that the same all the way throughout the whole fall. But we're going to start modeling this as it starts to accelerate. So we initially have a velocity v 0 equal to 0 meters per second. As it starts to accelerate and we have some velocity, we get some air going around this ball, and it starts to cause a drag force. And that drag force will increase over time. So if we go to a second point in time, we get a little bit of drag going up. And as the drag increases and increases, that's increasing because the velocity gets greater and greater. So you have more particles going around this ball over a given period of time. And it reaches a point where the drag force is equal to your force of gravity. And that point where drag force is equal to your force of gravity is what we would call when terminal velocity is reached. It's not going to be accelerating anymore. If F drag equals Fg, then we know that F net, the net force on it, in the y direction is 0 newtons, and that means our acceleration is 0 meters per second squared, so this object is not going to be accelerating anymore. We've reached the maximum velocity, and that's terminal velocity. So how do we solve this? Well, we want to get a function of velocity as a function of time. So let's just do a quick graph to see what this would look like. So we can see what we should get for a mathematical function. If we look at our initial position here, the velocity is 0 here. We said velocity is 0 meters per second. And if we put that on our graph, we'd have a 0. I'll switch colors here. And then what's happening to our velocity? We have a large acceleration. Fg is going down. There's no force going up. This is the largest acceleration. A is large. And on our velocity versus time graph, that's a steep slope. So we're increasing. And then as we get some drag, our acceleration decreases a little bit, but we're still accelerating here because force of gravity is greater than our force of drag. So at this point, later on in our graph, we have a little bit less of a slope, and then even less of a slope here. And as we end this, our slope would be horizontal. When our acceleration is 0, the slope of the velocity versus a time graph should be 0. And so we get a graph that looks like this. See if I can sketch this in here. I'll get yours closer than that. And it flatlines here. And where it flatlines, we call that the terminal velocity. And so this point right here would be terminal. And it won't, mathematically, it won't ever reach this. This is an asymptote. But in reality, it will reach this terminal maximum speed there and won't speed up anymore. What is that terminal velocity? Well, it depends on what this drag function is. So you'll get some equation for that drag function, and you could set it equal to your force of gravity function and solve for that terminal velocity. So let's do that. Let's take a look at an example. So an object's released from a large altitude from rest and experiences a drag force due to air resistance right here. Force equals negative b times v. This looks very similar to our boat problem, negative b times v. Let's go ahead and solve this particular problem to figure out what an equation for the velocity of the function is of the object as a function of time. But first, let's determine our terminal velocity. The terminal velocity of the object is going to be at this position right here, where your drag force is equal to your force of gravity. That's when we're going the maximum speed. So in this case, this is our drag force, and we're going to set that equal to the force of gravity, and we can calculate our terminal velocity. So our first step, F drag equal to F g, force of gravity, and your drag force in this problem was negative b times v, and that equals m times g. Well, this is my velocity here, and the velocity at this point in time has to satisfy this equation where your drag force is equal to your force of gravity. So that means this velocity, if I solve for v here, has to be equal to m times g over b. And we're going to drop out this negative here because we're just comparing the magnitudes of those two forces to get our answer here. And so the velocity, this will be our terminal velocity. I'll call it v term. Terminal velocity is going to be mg over b. And so I could go back to this graph here, and we can label this terminal velocity mg divided by b. Okay, that's how you calculate terminal velocity. That's pretty simple. Now, the hard part is to derive an equation for the velocity of the object as a function of time. We're going to do the same thing that we did in the last problem. I'll do that on a separate page here. We want to do our acceleration is equal to our net force on the object divided by its mass. And the object had two forces acting on it. Force going up, our drag force, which is Fg, which is negative b times v, and our force of gravity, which is a constant, m times g going down. And we'll define downwards as the positive x direction, which is different than what we normally do, but we're going to do that so that we're accelerating in the same direction. Our velocity function will go up instead of down, negative values, so we'll keep everything positive here. And if we evaluate at any point in time for this object, it's going to change for all of these points in time. If we evaluate the net force, all we do is we take Fg minus our drag force, Fg minus drag force, Fg minus drag force. We get 0 here when they're equal, but it changes all the way throughout the problem. So we have a changing force, and our changing net force will be plugged into this equation here, net force mg in the positive direction minus b times v over m. That's your first step. Now we need to make this look like a differential equation. To do that, we write our acceleration as the derivative of velocity with respect to time. That equals mg minus b times v over m. And now we have to separate our variables. We want dv and v on the same side, and we want dt out of the denominator. There's a couple ways to manipulate this. Some will have you plug in terminal velocity first. We'll just evaluate it with the variables just as they are. So I'm going to take all this on the top, mg minus bv, and divide by it. So I get dv over mg minus bv equals, and then dt goes to the other side. So I get 1 over m is left on this side times dt. And now I've separated my variables, dv and v. This is just a constant, so it goes along with my bv. The reason it does, you can't just divide by v here and get v on the other side, because then I'd have a divide by v right here in my mg term, and we wouldn't have separated our variables. So we've got them separated here. I can integrate. I'll integrate this side and integrate this side. The integral on this side is pretty straightforward. The integral on this side, I'll do it over here. We get to do little u substitution here. Dv over mg minus bv. So if I want to integrate this, I want to try to make it look like this. Du over u, because I know the answer to that. Integral is natural log of u. So to do that, let's call the bottom u. U equals mg minus bv. Du would then be the derivative of this. This is a constant, that's going to be 0, so it's just negative b dv. And then I can solve for dv here. dv equals negative 1 over b du. And that can be substituted in for my dv. My u will be substituted in down below, and I get the integral. Dv is negative 1 over b du over u. I can bring my constant out, negative 1 over b times the integral of du over u. And this would give me natural log of u. So the answer here is negative 1 over b natural log of u, and u is mg minus bv. So we substitute back in. So that's my answer on this side, negative 1 over b natural log mg minus bv plus a constant c. We've integrated this side. This side is just a constant. The integral of dt with respect to t is just t, so we get 1 over m times t plus c. Again, we can combine our c's like we've done before. This is c1 and c2. Just subtract c1. And this is just a constant. We'll just call it c here. These drop out. And I get negative 1 over b natural log mg minus bv equals 1 over m t plus c. To solve this, I'm going to get rid of our 1 over b on this side, so multiply both sides by negative b, and I get natural log mg minus bv. Multiply by negative b, I get negative b over m times t. The constant is just a constant, even if it's multiplied by another constant, so I'm just going to say plus c still here. I get rid of the natural log, take e raised to power both sides, mg minus bv equals e to negative b over m times t plus c. And I'm going to separate this out again here. Let's do this first. So let's get v by itself. We want to solve for velocity as a function of time, so we're going to get v by itself here. So I'll subtract mg, bv equals e minus mg, and then I'll divide by negative b. So I get negative 1 over b, e to the negative b over m t plus c plus mg over b. Well, this should look familiar to you. We just solved for this. That's our terminal velocity. So if we go back here, we solve for terminal velocity mg over b, and we got that from this relationship here. So I could write this in here. This is just terminal velocity. So let's keep simplifying this. I can also write my first term like this. So velocity is a function of time. We're almost there. Negative 1 over b times e to the c power times e to the negative b over m times t. Add powers, you multiply the variables, plus v term, our terminal velocity. Well, this is just a constant. So let's just call that c, and we're going to figure out what c is, and we're done. vt equals c times e to the negative b over m times t plus v term. How do we figure out what c is? We need to know an initial condition. And our initial condition for an object that gets dropped from rest at v of time t equals 0 is 0 meters per second. So we plug in 0 for t, and we have 0 on our velocity side, so 0 equals c times e to the negative b over m times our velocity. 0 occurs at time t equals 0, so we plug in 0 plus v term. Well, this term right here is 0. Anything raised to 0, not 0, 1. Anything raised to 0 power is 1. And so I get c plus v term equals 0. So c is equal to negative v terminal velocity. And that means my velocity function, I'll write it over here, if we plug that back in, velocity as a function of time is equal to, c is my v term, so a negative v term e to the negative b over m times t plus v term. And you will see in the reading, this is written a different way. Substitute out the v term. You can write it however you want. You could also substitute in your v term. We know what this is. This is what do we get here? mg over b. So you could also write this without v term in there. We could just write mg over b for all of these. It doesn't matter. That's your velocity as a function of time. Okay. If you graph that, it's going to get larger and then slowly flatline. So if we look at this, let me pull it up, terminal velocity. This is what it would look like. It increases greatly as it's falling, and then as the force of drag gets greater and greater and greater, the velocity starts to flatline until it reaches terminal velocity. And you can play around with numbers, see what happens as you increase the mass. Well, if I increase the mass and have the same drag force, I can go faster. And if you change your b variable, that's your drag coefficient. It changes your graph as well. Small drag coefficient means that you're going to have to go faster and faster to stop that or slow it down. Oh, we're really big here. Oh, we're negative 0.1. So you can play around with those and see how it would affect your terms here. Let's answer the rest of our questions. Derive an equation for the position as a function of time. We know how to do that. We just did that on the last video. So take the integral of your velocity as a function of time. And you'd have to integrate what we just got and then solve for c. We'd get that. Derive an equation for the net force as a function of time. Well, net force is equal to your mass times your acceleration. Now, how do I get my acceleration? Well, this is going to be mass times the derivative, first derivative of your velocity function. So we could take the function that we just got, take the derivative of it, multiply by m, and it will get you a function of force with respect to time. And that function, your force should get smaller and smaller. Your net force will get smaller and smaller. We do have force as a function of velocity here, but not as a function of time. And this is how you get force as a function of time. And the reason the net force gets smaller and smaller is because your drag is getting larger and larger. Okay, so that's it. That's how you solve those problems. What actually happens in the real world for small or relatively low velocities, your drag is actually related to the square of the velocity, and that is a much nastier equation to solve. It's in the reading that I gave you. You will not ever have to do that on an AP test, so don't worry about that. The only problems on an AP test are directly proportional to velocity, and those are the two types. You'll have drag ones or the boat ones. Okay. I do want to show you this just so you can be aware. If you look at this is on your little worksheet. I want to walk you through this so you can see how you get your points on a free response for this. This would be one like the boat slowing down. It's just a block on the surface and there's just one force resisting it. And if you look at how they get their points here, this one is asking you to set up the differential equation. They get 1 point for just substituting correctly into Newton's second law. So they put both their forces in Newton's second law and they get their point. They get 1 point for turning A into velocity. Derivative of velocity is a derivative of time, dv dt. That's a pretty easy point. No hard math there. Determining the terminal velocity, we did that. That's when your force resistance is equal to your drag force, or your drag force is equal to your gravitational force. And they do that here and they get their terminal velocity, pretty easy point. And then how do you solve your differential equation? Watch where the points come from here. They set up their differential equation. That's from the previous part. They separate their variables. All you have to do is get v and t on the same different sides. d, v, and v on the same side, and you get a point. If you write the integral sign on both sides, you get a point. Just take the integral. Then you need to demonstrate substitution by using initial final values. All this is saying if you use your limits, you're plugging it in here. If you're not using limits, this just means that you're going to solve for c correctly. At the end of it, you get a point for that. You get a point for attempting to solve for your velocity. So after we take the derivative or the integral, if you try to solve for v on one side of the equation, you get a point to solve for v. And on our equation, that would be getting down to this part right here. We've taken the derivative or the integral, and we're just going to get v by itself. I get a point here, even if I did it wrong. I get a point for showing that I'm attempting to solve for velocity as a function of time, and then you get 1 point for the correct answer. So this is a 5-point problem. 4 of the points are just for showing their steps. No correct work. The last point you get if you did it all correct. So it's not terrible to be able to get all your points on a problem like this. Okay. And that's it.